So let me again share my screen if I can. Let's see.
Bir soru daha yok muydu hocam quizde?
Quizde bir soru daha olamadı. Çünkü aslında 5 soru hazırladığımı düşünüyordum ama 4 soruyu bulabildim. Bir soru galiba kayboldu, bilmiyorum. Dün gece biraz geç hazırladım da belki de 5 soru hazırladığımı düşünürken 4 soru hazırlamışımdır. Ama 4 soru vardı yani. Onu da kapattık. Alright. So now we come to basically the let's say design of PID controllers. Okay. Controllers in practice, let's say. By the way, I find this root locus analysis very useful. So, in particular, in order to really well understand how different actions actually contribute to the overall performance of the controller. Okay, and I have put 3 video assignments of this, I would say, very useful guy from the internet, another instructor in process control. He has a very practical view of things and actually discusses PID controllers very nicely in those 3 videos. So I would urge you guys definitely to go over these 3 videos as well. Now we will move on to different ways of designing PID controllers. Actual design, meaning that obtaining exact controller parameters for a given set of specifications. Okay, so we can say in industry as well. Okay, so this would give us information about a number of techniques that are widely used in industry. Some of these techniques, in particular what we will call open loop testing based design formulas, we will actually try to derive them because we often find it very difficult to accept things that we cannot mathematically verify. So I will try to go over the derivation of some of the PID design formulas. Okay, so if we wanted to kind of categorize this design space, we can talk about, let me use my real estate a bit more conservatively. One category is known as open loop testing. Open loop testing based design. Okay, based PID design. Okay, so this is often known as process reaction curve method. Okay, so you will hear this terminology as well. So the logic behind this is that you take the plant, you apply a test signal to it, often a step function, and you measure the response of the plant, and you fit a model to the plant, and from this model you design your controller. Okay, so if the plant is linear, okay, if you can obtain a linear or linearized model, we will have available for us all the tools that we know. Okay, all tools. I mean, from 302, for example, all techniques. Now, if the plant is nonlinear and cannot be meaningfully linearized, this is particularly true if the system has a time delay in it. Okay, so in this case, we use the first order plus dead time nonlinear model. So let me put a note somewhere. Notes. FOPDT means first order plus dead time. Dead time is another name for time delay. Okay. So in that case, you can fit a first order plus dead time model, and we will cover this in detail. And based on this model, there exist a number of design formulas, and hopefully we will derive some of these formulas. Okay. So for example, you will hear things like Cohen-Kuhn design rules. These are 1953, okay, 1953, so rather old. Also more recently, there has been other derivations. ITAA, for the proportional controller, and internal model control for the PID controller. These are more recent, 1989, I believe. Okay, so these formulas we will derive in detail mathematically where they come from. But once they are derived, let me tell you, these are design formulas. They are tables which are parameterized based on the parameters of the first order plus dead time model. So once you fit this model, this nonlinear model, to your plant, the design tables basically give you straight away the PID controller with a certain guaranteed performance. Okay, so this is like a starting point, and you can still fine-tune the parameters based on looking at the response of the plant. Okay, now whenever you are actually modeling the plant, there is a concept called testing the plant. Wire out to wire in. And I will maybe come back to this concept later on again. Maybe I'm going to sketch it. Oh, let me sketch it here. What does it mean to have a wire out to wire in? Okay, so if there is the plant here, okay, plant, and there is an input to the plant, U of t, and there is the output of the plant, and here is your controller, okay, plus minus, and here is your controller. Let me write it verbally here, controller. Okay, so the model should be from wire out. This is wire out. So the point where you are going out of the controller, including everything, if we think about this as your controller block, so everything happens, and here you have a wire in. So that means the plant output actually comes in. You have sensors here, okay, whatever extra elements, okay. So all of this thing should be included in the model, everything that the controller sees, okay. So everything the controller sees should be part of the model. Any delays, any extra effects, communication, whatever, part of the model of plant. This is known as wire out to wire in. So this is called wire out to wire in model of the plant. So it's just including everything from the controller output to the measurement coming into the controller. Okay, is there any questions here? Testing the plant wire out to wire in means you need to develop your model that takes into account everything that is outside of the controller. Okay, So another branch here is, instead of open loop testing, that means taking in the plant and applying a test input and measuring the output, fitting a model, there is also the category called closed loop testing. Closed loop testing based PID design. Okay, so what is this? This means test the closed loop system with the controller, record behavior, tune performance. That means you will test the system in the presence of the controller while you are fine-tuning the parameters of the controller. Okay, this can be done manual with rules. In fact, this has a particular name. It is called Ziegler-Nichols continuous oscillation or continuous cycling method. Continuous cycling or oscillation method. This has been developed very early, actually, 1940s. Okay, it's a very influential method because, as we will see, and we will take a look at this in detail, this actually can be done manually, and you resort to some tables that have been developed with a large number of experiments, and you can achieve very reasonable performance without resorting to any models, any mathematical design techniques, and so on. That is why it's a very popular method. There is also a more recent iterative optimization based methods. Okay, so if we want to order in which order we will look at these things, I will first very briefly discuss the iterative method. So that's going to be our first kind of coverage. Then I will cover in detail the Ziegler-Nichols method of continuous oscillations, and then we will spend some more time in the open loop testing part. Okay. So now, any questions here related with this set of techniques that we will cover? All of these methods will give us essentially a full PID controller, or a P controller, or a PI controller, or a PID controller, okay? With numerical values assigned to each one of the controller parameters. So it's different from the root locus technique because in the root locus techniques, our primary motivation was to actually gain an insight into the effect of the different parameters. Here, we will essentially aim to obtain a fully functional PID controller in the end. Okay, so let's say one, iterative optimization. I will just give you an idea about this technique, but I will also put out a video example of how this is being used in industry. Okay. Now this technique is very recent because it heavily relies on computer based controllers that can experiment with the system very quickly with different controllers. Okay, so the basic idea is that there is the controller in a closed loop system, but the computer adjusts the parameters of the controller and runs the system with that controller and measures the performance of the overall system based on some predefined performance measures. Okay? And then the computer uses an optimization algorithm in order to fine-tune the parameters in order to better and better the performance of the controller. Okay? So the idea is to define a performance measure or function to measure quantitatively the closed loop system performance use a computer based optimization procedure to iteratively let's say fine-tune controller parameters. Okay, let me give you an example. This measure often is called an objective function. The definition of the objective function or a cost function is subject to debate and subject to research. Defining this function often becomes part of the problem. Example, it may be, for example, the integral of error. How? For example, you can apply a step input to the plant. Let's say this is your R of t, and let's say this is your response function. Okay, let's say the system responds like this. If you take the integral of this error between the reference and the actual, okay, so this is your integral of error. You can see that as the response approaches the ideal step response, which directly coincides with the reference, the integral of the error actually approaches 0. So the minimum value for this integral of error objective function is equal to 0. And it increases as the response becomes worse and worse. Okay? So the procedure, the computer-based procedure, will try to minimize essentially the cost function j as a function of these PID controller parameters. Okay, tau d subject to other constraints. You can also put other constraints like actuator constraints and so on and so forth. Okay. So this, by the way, is the topic of topics of some of the courses in our department. In particular, Ee407, which is the optimization course, and the specific application to control theory is Ee454, which is called optimal control theory. Okay, so if you're interested in this field, there is quite a bit of graduate courses that you can take later in your education. Okay. So this obviously requires either an accurate system model. If you want to do this in simulation, you need an accurate system model, and you will put the controller in front of the system model, for example in Simulink, and the optimization algorithm will play around with the controller and very quickly simulate the overall system, calculate the objective function, and iteratively fine-tune the parameters to achieve the best objective function. Okay, an accurate system model and time solution of the error. Time solution of the error. Obviously, if you simulate the system, you obtain the time solution of the error numerically. Alternatively, you can experiment with the actual system, okay? In which case you need the ability to continuously experiment with the system. This is known as hardware in the loop. Hardware in the loop. In the loop optimization. You will hear this term frequently. Hardware in the loop means you automatically experiment with the system while trying to optimize certain parameters of the system. Okay? Or basically you can also have a closed form system model where again this J as a parameter of Kc tau I and tau D can be obtained mathematically. Okay, in this case you can perform the optimization in closed form rather than with a computer. In this case, remember you can basically take the derivative of this function with respect to Kc equated to 0. You can take the derivative of this function with respect to parameter tau I equated to 0, and similarly you can take the derivative with respect to tau D equated to 0, solve the resulting equations, and you have a chance to find optimal parameters. These derivatives equated to 0 are known as necessary conditions. Unfortunately, they are not sufficient conditions. Necessary conditions. Any actual solution needs to satisfy these equations, but all the points that satisfy these equations may not necessarily become your optimal controller. And as I said, all of these things are discussed in details in the graduate courses that I've just mentioned. Okay, so that kind of gives you an idea about what this path looks like, but obviously it doesn't give you sufficient information to go ahead and in fact, you can go ahead and try it anyway, but at least mathematically, it's not sufficient information to understand all the bits and pieces of that path. Okay? Is there any questions at this point? Because we are going to conclude this part of our this is completed at this point, and I'm going to move on to the second category, which is the Ziegler-Nichols continuous cycling method, which we will study in more detail. Any questions? Arkadaşlar, soru var mı?
Hocam dersin bu içerikle alakalı değil ama homework'la alakalı bir sorum olacak. Benim onu sorabilir miyim?
Şöyle, dersi bitirelim o zaman. Ben title'ı atayım. Let's say up next, which is tomorrow at 9:40 is basically we will cover Ziegler-Nichols continuous oscillations method. Okay? Başka